All right, we're back. So we've been working on this OpenGL project, and we started with the cube example from the OpenGL package documentation, and have been slowly modifying it. So we have multiple cubes. We've understood a bit about how to pass data with the uniforms and things like that. So my next goal here is to get each of these cubes to rotate at a different, with a different offset. So to do that, I guess we basically did this earlier. We can just have a different angle for each one. So I'm going to have this based actually on the, not the X position, but the Y position. So let's put all these first. And then here for Y equals 1, we will add 1 to the angle. And maybe we should add like 0.2 to the angle. Yeah, there we go. And this one will be at minus 0.2. Or actually, why don't we do this? Why don't we multiply? So this will be at 0.8, and this will be at 1.2. Cool. So we know we can control these independently. So what I'd like to do next is try to use the animation package that we used yesterday and see if we can add easing, like a custom easing, to these rotations. And actually, I kind of want to understand where this angle is coming from. So scene, where is that used? That's used here. Ah, right. And the value for that is coming from our model. So let's refactor that a little bit and make a type alias. So our model right now is just a float, and our scene takes a model and gives our list of renderables. Then, let's see, where else are we? Where did scene get used? Scene got used in main. Okay, and this was defined at the top. And then our initial model is 0. Let's pull this out to a separate function. Update takes a message and a model and gives back a model and a command. And for now, our type alias message is also a float. So actually, let's make a real message type. So message, we'll call this tick, which takes a float, and we get a tick message from our animation frame. Then we'll do a case message of. This is now called message, and if we get a tick, we get our DT. Whoops. There we go. Okay, so we've slightly refactored that to fit our standard Elm architecture pattern better. I guess let's do one other refactoring. Let's take our meshes and put these in a separate file. So that's kind of a big chunk of code. So I'm going to make a new file here, call this meshes.elm module meshes, And actually, the only thing we want to expose is cube. And we're going to need some of these imports. Let me just grab them all for now and delete the ones we don't need. Oh, do I not have warnings turned on? Let me check my elm-linter package. Report warnings. Yeah, cool. I'm going to turn that on. Okay, so we don't need this. We don't need this or these. Great. And then face is just a helper function in here that's used by cube. And then now it can't find cube, so we're going to import meshes, exposing cube. And it can't find meshes because we're in a separate folder. Interesting. Okay. So we actually need to call this day 6 meshes and then rename the folder to be day 6. And then the module name. Okay. And it still thinks the module name is messed up. I think the compiler is just old. So I'm going to remove Elm stuff and run it again. And, did I not save this file? day6.meshes. So what's wrong here? day6/meshes. According to the file's name, the module should be this. According to the source code, it's called meshes. Oh yeah, here. How did I mess that up? Oh, okay, that's a bug in Atom. It doesn't keep track of when you rename files. Okay, there we go. Okay, so we just did some minor refactorings. We pulled the cube mesh out into a separate file and added type aliases and a type for our message and for our model. Let me pull this one up to the top. And color is unused in here. Okay. Cool. So next up, let's install the animation keyframe package, or what exactly is the name? It's mgold, elm animation. Yeah, so let's grab this package, and we can use this to use some easing functions and actually to specify delays and things like that for the animations. So I'm going to elm package install that package. Okay, great. And then start up ElmLive, the dev server again. Now, we want to use an animation to control this angle. So let's make this animated angle. So we're going to import some things from this package, this animation package. Import animation exposing. Let's just expose everything for the moment. So one thing we get is an animation, which takes a start time. So actually, why don't we set that to like let's see, how fast is this actually changing? I guess this is in seconds. So let's start it at 1 second. And then we're going to animate a value, the angle value, from 0 to 360. Or let's just go to 90 to start with. And the duration will be 1 second. And that should be all we need. Then I think, then we use animate and give it the time. So this is the angle animation, and then the animated angle is going to equal, and actually we can call this t from the model. Then the angle is going to equal animate with t, our angle animation. All right. Okay, not quite what I was expecting. I think the values are actually probably incorrect here. Maybe we can animate from 0 to 1. So it seems to be waiting longer than 1 second. And then it started to turn. And then it stops. Okay, so we got something happening. The biggest problem here is I'm not quite sure what the appropriate range is for all of these things. So let's see if we can figure out what range the angle is supposed to be. It's probably going to be in radians. And uniform, so this takes the angle. So let's just use the angle directly. And all right, it's turning. And it turned by some weird fraction of a thing, so this probably is in radians. So we can convert this by just saying from 0 to degrees 90. Whoops, degrees. Oh, hey Quickly, welcome to the chat. Okay, cool. So we have it, we can control it in degrees now. I think the time values are also confused. So let's use time in terms of seconds. So I think we want this to be 1000 here because the DTs that we get from animation frame should be in milliseconds, I hope. There we go. Okay, so that seemed more like 1 second. All right, so we've normalized all our units, so I'm feeling better about that. So now, let's animate. Okay. So now what I want to do is give these different delays. So each of these angles, I'm going to put in parens and add a parameter d. And then for each one of these, we'll take the basic animation and delay it by whatever the delay amount is. And the delay should be in seconds. So I guess here we want to delay by 0.4 seconds. And then for this one, we'll maybe delay by negative 0.4. And then for these, we'll delay by 0. Yeah, there we go. And then let's have this do a full spin. Nice. Cool. So maybe we can do something a bit nicer with the colors here. I guess one thing we can do is have the entire cube be a single color, or based off of a single color. So why don't we have cube take a color, and we'll use that in place of all of these. Actually, I can grab these, do it that way. And then our main shouldn't compile. So now we want to give a color to each of these cubes. So let's go import color. And then we'll have a red one, green, purple, yellow. Okay. So we have cubes. Probably the right thing to do, like I want these to have shading, so probably the right thing to do would be to have a fragment renderer that would do lighting somehow. But I think that's a bit bigger than I can bite off for today. So I think just in the mesh, we can define different colors for the different faces. And I think there's some functions in this color package that we can use to make different colors. Oh, there's just a light. Okay. So I'm going to define another color here, which will be, let's see, and let's also get the HS, or what is this called? The hue, saturation, and lightness. And the alpha is color.toHSL of the color. And then lighter is going to be color.HSL or HSLA. And we'll stick these back in. Color.HSLA of the hue, saturation, lightness, plus what units are these in? They're from 0 to 1. Okay, so we'll add a 0.1 and alpha. And darker is going to be color HSLA, hue, saturation, lightness, minus 0.1. And let's see. My CPU seems to be going crazy, so let's see what's going on here. Uh-oh. OBS is having problems. Looks like the stream probably dropped out. Alright. Let's try killing that. And starting up again. And our Chrome helper is also having problems. Okay, it looks like the stream upload is back on track. I think this tab is having trouble. Okay, there we go. I think that just dropped a bunch of frames on the stream. Sorry about that. Yeah, there might be some problems with the way I'm using this that's leading to performance issues if I let the tab run too long. All right. So let's continue with this then. We're using our new colors. So let's put the darker ones on the back and bottom, and the lighter ones on the top and the left, maybe? Let's see, so this one's the bottom, this one's the left, and the front is this one. Or no, we want the top one to be lighter. Yeah, there we go. That is shading it properly. There's the animation. Cool. Cool. So let's see. So let's recap. So we took our, so we have our meshes file, which defines a vertex type and then cubes, which produce a triangle list of vertexes. Then let's see, I think, well, if that tab is not what's having performance problems, I'm not sure what's going on. But my whole computer is suddenly grinding to a halt. Okay. So our recap again. So then we define a scene, which takes our application model and gives a list of renderables. So we get that by using render from the WebGL package with our shaders and our mesh definitions, which is noted in the README. You don't want the mesh definitions to change every time because they have to get sent to the GPU whenever they change. So this potentially might be a problem with the performance of what we've written today. An alternate thing we could do is pass the color in as a uniform for each cube, and then we would only have the same static mesh. But these function calls should be cached. I guess that's probably not happening the way this is defined. So we should probably define these as variables and then pass them in. So potentially that's the performance problem that we were just seeing. Each one of these is calling the cube function each time and generating a new mesh instance, and then the WebGL package can't optimize it, and as a result it has to resend the mesh to the GPU on every frame, which would be a bad thing. So if that's what's happening, then that would definitely account for the performance problems we're seeing. Then we have our uniforms, and these are just the small pieces of data that are going to be used by the vertex shader, and they can also be used by the fragment shader. So then looking at, okay, so here's our uniforms where we define a bunch of different matrices that are going to be applied to transform points. And then the shaders themselves are some short little GLSL programs which pull these variables out of the records. And here we get attributes for the vertex that we're rendering. We get our uniforms, and then we are going to output two things: the GL position, which is where the point will actually render, and this V color, which is going to get sent to the fragment shader. And then our fragment shader receives no attributes. It receives the uniforms, and it also receives the V color for the point that was produced by the fragment shader. And then it has to return the color to render the point in. Cool. So I'm actually going to try this refactoring really quick and basically pull these up to top level definitions. And I think the way I'm going to do that is make a record called cubes, which is going to be red equals this. And then let me just duplicate this a bunch. We have blue, green, purple, yellow. So this one's blue, this one's green, this one's purple, this one's yellow. And then here, rather than calling this function every frame, we're just going to refer to cubes.red, and the same thing here. So I think this should dramatically improve the performance. So that looks better. If we leave this tab open for a minute or so, hopefully we won't see my whole computer crash to a halt like it was a minute or two ago when we were running this. And yeah, so this is why I didn't have warnings on most episodes, because it forces you to put type annotations on everything, or else you get these warning bars. Cool. Yeah, okay. So my Chrome is not grinding to a halt like it was before. So I think that was indeed the problem, and was something that was noted in the WebGL Elm package README, saying that you want to make sure your meshes aren't changing very often, if they change at all. So, cool. Well, I think I'm going to keep this kind of short for today. Since I'm going to be continuing to do quick streams every day for the rest of November, and then get back to doing some longer episodes in December after that. So if you aren't able to catch the streams every day, I will be posting these up on YouTube again, as long as I don't have more trouble with their automated flagging system. So thanks for tuning in today. And yeah, if you're doing any creative coding projects, especially if you're doing them in Elm for Codevember, be sure to let me know on Twitter. And this code will be posted up at the link in the bottom right corner fairly shortly. And hopefully we can, over the next couple weeks, dig into more sophisticated stuff with some of the WebGL shaders and see if we can do something fancy with that. So with that, I will leave it here, and I will see you all next time. So thanks for tuning in. Bye.